is 8 o'clock, and I was putting a calendar here on the board because the last time we were together, I said, hey, I want you to give this some thought in terms of the schedule and where we're headed. The syllabus had us, or has us, I should say, scheduled on the test on the 16th. And of course, today here is the 4th. And so what I'd like to do is continue to do some more examples into chapter 6 and then get started with 7. And actually 7 and 8 kind of blend together. So you'll see the lecture on 7 and 8. It's kind of hard to distinguish where kind of 7 ends and 8 begins. And I'm going to be merging those two together. But I'd like to get started on that 7 and 8 and then maybe kind of talk about it here and then start doing examples in 7 and 8 here and even flow into here, which is why I'm thinking moving the test makes the most sense in that. It gives you a little more time to be prepared. The one negative thing is it might move it to where you have other exams, and I didn't know that. That's why I asked you to think about it. The feedback I had gotten so far is that it did not make things worse. It made things better to move it. And so in a minute, I'll ask for a show of hands. But because of that, I'm thinking this makes a lot of sense here to move it back. If not, I suppose we still could fit this in. It would make 7 and 8 a little rushed. And Wednesday might be a good day, but like I said, I kind of added the picture because I like to use that overflow room and gives us more room. So with that said, by a show of hands, who would be in favor of saying, let's just move this 1 week into here on the 23rd? Okay, that's what I was thinking. Anybody really opposed to the idea? Because I could probably work with you on that also. But it sounds like that's the best way to do it. So let's plan on that. Change your calendar. We'll put the test on the 23rd. The game plan then will be, as I was beginning to say, is let's do some more examples from chapter 6. We'll get 6 out of the way. We'll even get a chance, I think, to start 7 today. And so we'll talk about 7. And 7 and 8, the lecture material, I'll just kind of merge together. And so then we'll start doing examples from 7 on this day, the 11th. Then we'll do examples from chapter 8 here on the 16th. And then we'll actually get started in 9 then and get a little bit of work done with 9 on this Wednesday, even though, of course, that won't be on the test. Then you'll take the test. And then that way, then on the 25th, we can finish up chapter 9 with examples so that we have a good start and almost a completion of chapter 9, because I think having spring break and that extra time to look at chapter 9 is good, because the longest chapters, I guess I should say, longest chapters is 9 and 10. I'm not sure which one is longer there, but the long chapters of the entire book, I kind of wonder if the author shouldn't readjust both 9 and 10, but particularly 9 into 2 chapters. It's just a lot of material. Not an unreasonable amount, though, so that's just what it is, and that's what we leave it. But that's why I said spring break always falls at a good time, obviously in the springtime. Those who take it in the Physics 121 in the fall don't get that extra week in the spring. But that extra week in the spring falling right on our 2 longest chapters is a good timing with 9 and 10. Okay, well, with that said, I'll just kind of leave that on the board as people come in. You can spread the word that we'll push the test back 1 day, and that'll be the plan up until spring break here. Let me go ahead and then turn on the overhead and get the PDF of the book started here, because as you know, we were working with examples and we had done circular ones so far, and that's it. I want to do 2 more circular ones just to kind of make sure that well, maybe I'll just put it right here for a second. A couple more circular ones, just to make sure that really sets home with you, and then we'll move on to the other two cases. Because remember, Chapter 6 was really just Newton's laws continued, and now we've done quite a bit of time on Newton's second law, so I hopefully it's sinking in. You did a whole chapter on Chapter 5, and then this chapter was things going in a circle, things in accelerating reference frames, and things that had resistance forces. And so I haven't really done any of the accelerating reference frames or the resistive forces. But the other two I have on the list here were 61 and 53. And so let's jump here to 61 and start with that first step. Got a good physical picture of what is going on. And so again, kind of read it, and as you read it, hopefully interpret some of the numbers. But here we have what I might call an old school model airplane, where the airplane is actually tied to a tether or a wire. This is not a remote control one. In fact, maybe I should kind of review. You may not be familiar with this toy because, like I said, they probably haven't existed for a long time. But when I was a kid, this was one of my favorite toys, and it was a little airplane. And a little airplane on the end of a wire, and you would start the little motor, and then you would run over to the circle of the wire, and then you can control the airplane via this long wire. And so it'd go around, and then it would take off, and eventually you'd get it in the air. And you had these little control wires, more like a kite than a remote controlled drone that you would see today. So here's the model airplane, and of course what makes it a little more interesting problem is that besides having the effect of gravity and what we'll call the lift from the wings, there is actually the tension in the control wire, and so there's an added force that you wouldn't have had if you didn't have the control wire. So I still like it as a problem, even though, like I said, it might be an old school toy. But I take all of that length to give you a good physical picture. Got the idea of what's going on? Somebody's standing in the middle of a field, they've got an airplane at the end of a wire, and they're controlling it. In fact, let's read a little bit more here. It says a model airplane of mass 0.75 kilograms flies with a speed of 35 meters per second in a horizontal circle. Now let me stop there, because again, this is going to play a big role, this physical picture. Where is the airplane? Where is the person holding the wire from the airplane? So again, if I'm that person, the airplane is up here at an angle, and the airplane goes in a circle. Now the circle is not ground level, the circle is above me, but it's still a horizontal circle. Fair enough? And that's an important part of this, and that's why the author says it's a horizontal circle at the end of a 60-meter, wow, that is a long wire. I never had one that long, but a 60-meter control wire. Compute the tension in the wire, assuming that it makes a 20 degrees, and so they kind of show in the picture, a 20 degrees with the horizontal. The forces exerted on the airplane are, and I'm glad he kind of explains this, partly because it's an old school toy that you might not be familiar with, and partly because it has an aerodynamic lift, and we haven't really done that yet in this class. We will talk about it at the very end here in Chapter 14. How does a hydrofoil and an airfoil work? But this would have to take you back to your Physics 102, where I know you did Bernoulli's principle, and you talked about an airfoil and a hydrofoil and those good things there. But here it says, these are the forces, the pull of the control wire, all right? The gravitational force. And then he goes to describe the aerodynamic lift that acts at a 20 degrees inward from the vertical. So again, if there's an airplane and as its wings cut through the air, the lift is perpendicular to the surface. So if the airplane is slanted a little bit, then what direction is the lift? Slanted a little bit, perpendicular to those wings. So that's an important piece to know before we can begin to apply our Newton's laws, because that's where the free body diagram comes into play. And so I think I've accomplished step number one, which is got a good physical picture of what's going on. Leading into step number two, let's draw out the forces. So we can go to step three, writing out the equations, and step number four, solving the equation. All right? And maybe I should come back to the question. The question, remember, is compute the tension in the wire. Okay? And so here is the picture they give. Actually, they partially give a free body diagram. Well, maybe they completely give a free body diagram because they do give the three forces involved here. I'll repeat them on the board, maybe not with quite as nice detailed picture as there is in the book. That'll be my airplane, just kind of a blob. What are the forces on this blob? Which, by the way, maybe this is a good time to point it out. I know we're not in chapter 9 yet, and certainly not 10 or 11, but if you'll notice, everything we've done so far has been just kind of a point-sized object. It hasn't really had dimensions, right? And so there's nothing about what we've done so far that would make a difference whether this airplane was, 30 centimeters long, 20 centimeters long, 100 centimeters long. Fair enough? I think you can imagine, doesn't it matter how big our objects are, where the forces are? Do you push at the center of the object or you push at the top of the object? And all that does begin to come into play. And that's where chapters 9 and 10 are. And so 9 and 10, we finally give our object size. As we begin to push on the front of the object, not only do we push it forward, but it begins to rotate as we push it. And so more complexity is added and coming up, but one step at a time here. So I will take my blob here and say, what are the forces on this blob? And of course, like any of these, go ahead and write down the force of gravity and everything touching it. So in this case, everything touching it, and maybe I should call this a side view, but everything touching it is really just this control wire, which then is angled down at 20 degrees because there is a person over here holding the control wire at an angle upward of 20 degrees. And maybe I shouldn't have put the person there because it gets away from the idea of the free body diagram. The free body diagram is just the object, just the forces. Forget about everything else. But I think that angle of 20 degrees helps. Now also, if I make a straight vertical line, then what we will call F, I think that's the symbol he uses. Yeah, F. Let's call this the lift of it. It is angled at a 20 degrees from the vertical. In fact, maybe you can probably then begin to see, and maybe you've seen these in movies, you'll see a lot where there's this pilot flying along straight and level, and now they're going to turn over to the right. Well, what do they do with the airplane? You're going to bank the wings, right? And that turns them over to the right. Why? Why would banking the wings then push me over to the right?
It's more force on one wing than the side.
I'm not sure I'd say more force on one wing, but right, I have a component that way, right? And so if I have a force, instead of going straight up, so when I was flying straight and level, the force was straight up. That upward force, the lift, was equal to the weight. The net force was 0, and so the plane went in a straight line. And as soon as the wings get banked, you now have the force, and if you think about the components of it, you now have a component to the right, and that's what pushes the plane to the right. So you're redirecting the direction of the force. By the way, what else is happening? It falls. Why?
Because now you're not enough force in the...
Right, exactly. So if there was just enough force straight up to equal the weight, and I bank the wings, now that force is at an angle, which is why I turn to the right. But the other side of that is now the upward component is not as large as the weight. So what happens to the plane? As he said, it falls. And so the airplane is going to do something like that as it makes the turn. And so it turns, but it also will drop. And so you got to be careful with that. Of course, in the movies, you usually see that as, you're making a turn to go down maybe in, hey, there's the survivors. And so you turn, and so you do want to go down to get a closer look, and you do want to make that turn here. Real danger would be a commercial airline, taking off. You go like this, and you're trying to get up. You're trying to lift. You make the turn too early and you start to drop, and you don't have much room to drop before you hit ground. So those are the dangerous parts of an airplane trip, is that landing and takeoff. Anyways, I get sidetracked there, but I think you see all the forces there, and so those are the three forces involved. Gravity and the two things touching it. One is the control wire, and the other is the air molecules that are pushing upward on the wing in a Bernoulli's principle that we haven't yet discussed. Which sets the stage perfect, because now I can write out the equations. But like any problem, we need to write them out based on a coordinate system. And so we have some decisions to make. And maybe I should kind of ask you to help me with that decision. What kind of grid do we want to put up here? Should I give it kind of a, what I'd call a level grid, where the x-axis is straight up and down? Or should I maybe tilt it so the grid is along the direction of the control wire? Any thoughts? And if you say tilt it, why?
Because that's the direction your forces are going.
Okay, I agree that's the direction my forces are going. Fair enough. But I said something very important in the last chapter that really you're going to see well in this one example is, where's the direction of the acceleration? And where's the center of the circle? Good. And I'll just repeat. You're right, the center of the circle. But where is the center of the circle in this case? And this is where step one is so important. A good physical picture. Where is center of circle?
Horizontal.
Yeah, center of circle is horizontal. It's right here. Here's the center of the circle. It's above the person right there. This is flying in a horizontal circle. The author made it very clear it was a horizontal circle. Right? And so again, let's come back to that physical picture. Here's the control wire. There's the airplane. The center of the circle is not where the person is who's standing. The center of the circle is straight above the person. That's the center of the circle. Now, keeping that in mind, then I do know that when I add up all these forces, there will be an acceleration, a radial acceleration towards the center of the circle. Now again, this should work out just fine no matter how you set up your grid. And I would agree in part with you that I look at the forces and I want to tilt this. However, since both of these summations, the sum of the forces in the x direction equal mass times acceleration in the x direction, and the other one is the y direction, if I set this up so that my axis is towards the center of the circle, then this becomes the radial component and this becomes the tangential component, and we know how to handle the radial component, and to me that is far more useful than it is getting the forces along the direction of the axis. Of course, both would work, and so I don't want to imply in any way that you have to set up the grid the way I would do it. But I do want to point out that I do think there is easier ways and harder ways to solve a problem. Even going back to the test we went over last time would be an example of that. That rocket, some of you calculated the time that it took the rocket to run out of fuel, and then the time it took the rocket to get it to its highest point, and then the time it took for the rocket to go from its highest point back to the same level that it ran out of fuel, and then the time it took to go from the same height all the way back down to the ground. And you would add up those times and you got the total time of flight, and then from that you got the distance. And all of those is correct, but the long, unnecessary, hard way. Okay? And so in this case, I would suggest we do an axis, and all the circular ones, we set up a grid so that if we ever know the direction of the acceleration, always put an axis along that way. That way you can directly say, that is the acceleration. You don't have to say, oh, it's the acceleration times a cosine, or the acceleration times a sine. And so use the sines and cosines for the forces. and not for the acceleration. I think that's a little bit easier. And because of that, I would say don't tilt your axis. Yeah.
Is that the same as the axis in this case?
No, good question. Maybe I should put a z-axis in my picture. I will put the grid on here. And so I guess I would suggest then that, and I guess the way I started to write it, tangential to the circle would actually be in and out of the board. So I guess this would be more of a Z direction. And then I would also have a Y direction. Yeah, which was your question. Good point. And so doing the axis like this would kind of fit that picture. And so now the Z forces would be along the tangential of the circle. And the Y forces are in my plane of my board. And then the X is towards the center of the circle. And so I happen to like that grid, and that's what I'm encouraging you to. And so it's I would say it's your standard grid, with the fact that maybe I changed the positive direction to the left instead of the traditional to the right. So that being said, now I can get to that step 3 and actually write out those equations. And so as I look in the X direction, which we just said would be mass times the acceleration in the X direction. The X direction is towards the center of the circle. So this would be the radial acceleration, which we know to be v squared over r. And so as I go to add up my forces, and I call this one T for tension, is that the symbol he uses? Yeah. I would say that this one towards the center of the circle has a T and then the adjacent piece of that angle, so it's cosine of 20 degrees. And also towards the center of the circle is a component of the lift from the wings. It is opposite of the 20 degrees. I suppose I should put in this picture the 20 degrees, but since we've tilted the airplane 20 degrees, the control wire is angled down 20 degrees and the lift is tilted 20 degrees. And so we would want the opposite of that 20 degrees. So we want the adjacent of the tension, and we want opposite of the aerodynamic lift. And of course gravity is straight down, so it does not have an X component. Just for a three-dimensional effect, since you brought it up here, the tangential to the circle would be, in this picture, the in and out of the board. In this more three-dimensional picture, it would be what you might call the thrust from the propeller, and then the drag of the air flowing over the body of it. And I'll put the thrust minus the drag. How's that? And that would equal to how the airplane is changing its speed. And they don't give me any information about that, so I hope I don't need anything about the Z direction in order to solve this problem. The Y direction is the other piece of this puzzle, where then as I take a look at this, I would have a component in the Y direction going upward. So that would be F cosine of 20 degrees. And again, notice it's the aerodynamic lift, and then I want adjacent to the 20 degrees. The other two are going down, or at least this is a component going down, and here's gravity where all of it is going down. So adding up these forces in the Y direction, I'm going to put a minus T, and the amount going down is opposite of that 20 degrees. And of course the other part going down is gravity, and all of it is down. And so those would be the three forces added together, the three components, or at least these two components that are vertical and then that one that is down. And so I add up those three and I set it equal to, and again, this is the advantage of not tilting the axis. What does that equal to? 0, right? This airplane does not accelerate in the y direction if it is truly going around in a horizontal circle. You take a snapshot right there. It's not going up, it's not going down. It is, of course, turning, so it does have an acceleration in the x direction. It perhaps is going faster or slower, depending if the thrust or the drag is greater, but they made it very clear it's a horizontal circle, it's not going up or down.
Can you explain the fourth and the
Yeah, maybe I should draw a top view of this. I mean, if you were up above the airplane looking down, maybe this person's flying it in a stadium and you're up at the top of the stadium looking down and it's going around there. Here is the airplane and it is being pulled in by the tension here, but the propeller here, maybe I'll try to draw an airplane. And it's being pulled inward that way. But you are getting then a thrust from the spinning propeller. The propeller grabs the air, puts a force on it, throws it back. So as third law, as the propeller puts a force on the air and throws it back, the air puts a force forward on the airplane. And here then, as the molecules flow across the cockpit and the body, there is going to be some drag. Maybe I'll call it capital R, since that's how we use the symbol here in chapter 6. So that would be the drag on it. And so again, as the airplane comes around right there, there is, of course, the pull of the wire, there is gravity down, there is the lift that's up at an angle, but then there is the forward and back to the circle, the tangential to the circle, as the airplane is trying to move through there. Does that help? Yeah. And so that would be the z direction. And again, this one, maybe more than any other problem we've done so far, is a good physical picture because it's very three-dimensional. And we always start with a lot of ours in 2 dimensions. And you can see that this equation is not even going to be needed. And so, you know, your author is trying to set you up for the easier stuff, the 2-dimensional stuff, the stuff that's a little easier to see. But as you brought it up, this really is a 3-dimensional problem. And so to understand what's going on here, I need to have that full picture in all 3 dimensions. And that will help me write out the equation. And if you look at this equation, you'll see that I don't need that z direction. Because as I study it, I can begin to see there are 2 unknowns here, and there are 2 unknowns there. And so I have 2 unknowns and 2 equations. Excuse me. In fact, let me get a little drink here. Wonderful tasting water. All right, so I think I've got that step 3 done, right? I've written out the equations, and now let's put in those numbers and solve it. And I might even cut this short and not actually solve it, but at least take a few steps where I can write in. And so let me continue to write in the numbers here, starting with this equation. And so they do tell me the mass of the airplane. So there is the 0.75. They do tell me the speed of the airplane. There's the 35 meters per second. Let me just confirm that. Yeah, that they say the speed is. And here's a big one too. It goes back to step 1. Good physical picture of what's going on. What's the radius of this circle?
Sine of 20 degrees.
Yeah, now remember they say the control wire is 60 meters. Is the radius 60 meters? No, absolutely not. And it comes back to that same question, where is the center of the circle? And so if this control wire is 60, then the center of the circle, or the radius, would be 60 times the cosine of 20 degrees. And so here I need to put 60 times cosine of 20 degrees in that step there. And now, maybe even getting my calculator out so I can change this to a number. I have a number here that is 0.75 times 35 squared divided by 60, and divide that by the cosine of 20 degrees. And so all of that is coming out to be a 16.3. And then that would have to equal these two, and I'll just, I should check the mode on my calculator. Okay, I'm in degrees. And so if I go cosine of 20 degrees, I can then write this as 0.9, well, I'll write it as 40 times the tension, and then plus the sine of 20 degrees, changing it into a decimal, would be 0.342 F, and maybe I'll put a little box around this, but there would be the first equation with just the unknowns written and everything else been plugged in. And then same thing with this equation here. I've got my cosine of 20, and so 0.940 times F would be this one, minus, and then there's the sine again of 20, so that's 0.342 of T equals, and if it'll be okay, I'm going to take the mg and move it to the other side and actually just put it in my calculator. So 0.75 times 9.8 is 7.35. And so there's kind of the first step of step 4, so we'll call it 4A, where I now have two equations and two unknowns, and everything's been plugged in there. Yeah.
Where did the 7.35 come from?
Oh, mg. So this is 0.75 for the mass and 9.8 for the meter, for the g. So putting that in. So again, just substituting everything in that we know, and then it looks more like a math problem at this point. And now we are at the place where I think you have plenty of skills to solve, given that you've done a system of equations since algebra or algebra 2. Algebra, probably a system of equations, yeah. So I know you can solve that. That being said, let's try my last circular one and then move on to some other things. How about number 53? And now I'm hoping that we've got to the point of these all look the same. Not that I want to bore you with another same equation, but I hope you're getting there saying, oh, yeah, this is obvious, come on. What are you doing? Well, you are realizing it's in a circle, therefore the radial acceleration is mv squared over r, and then just add up those forces. Exactly. When you begin to see that, you're ready to move on to the next step. And so we've done a lot with Newton's laws, and we'll do a little bit more here today, but it's time for you to put it into practice, and you have already with one chapter, and now this weekend you'll be doing the next chapter with chapter 6, and then we will begin to move into some more physics. Instead of looking at forces, we'll begin to look at energy. That's the next step we're about to do here in chapters 7 and 8. But number 53 is a lot like the one we just did. We have something going in a circle. Maybe you're familiar with this ride. I know Magic Mountain has one just like this. It's not one of my favorite rides, but it is kind of a fun one. It's, I like that Buccaneer right next to it a lot better there. But if you're familiar with the swings, you go in a circle and the swings swing out. Let's talk about this, because again, that step 1 is really important. What physically is going on here? And so it says an amusement park ride consists of a rotating circular platform 8 meters in diameter. So the author's got a nice little picture, 8 meters in diameter, from which a 10-kilogram seats are suspended at the end of a 2.5 meters. So here's these chains, massless chains. Which sounds kind of funny, but I think what the author's after is, let's not worry about the mass of the chain. By the time we put somebody in the seat and the mass of the seat, the chain is negligible compared to everything else in this problem. Plus, it'd make it a little bit harder, and we'll save problems like that for Chapter 11. Okay, so we won't worry about the mass along the chain, at least not quite yet. All right, it says when the system rotates, the chains swing out. They make an angle of 28 degrees with the vertical, so there's the theta. What is the speed of each seat? B, draw the free body diagram when you have a 40-kilogram child riding in the seat, and find the tension in the chain. Well, let's just start with A. What is the speed of each seat? And so I'll draw a little bit of that picture. Here's this giant platform circling around. Here is the seat angled at 28 degrees. And it makes this big circle going around. And again, like the airplane one, let me ask you this. Is this a horizontal circle? Is this a vertical circle? Is it a circle tilted like an incline? It's a horizontal one, right? And where's the center of this circle? Yeah, and so if you can imagine that being the path the seat is going to make, then this right here is the center of the circle, and that is the radius of the circle. Okay? And again, that's going to come into play as we put in our numbers. So that first step is important, a good physical picture of what's going on. I've got a seat. Yes, it's swinging out, and it is going in a circle. And its radius is right in the center of this column that is holding up the whole ride. Okay? And that's an important piece in this. Because once I know that, then I think I can take that next step and say, all right, if I were to write out the free body diagram and say, okay, here's the seat by itself, what are the forces on the seat? Well, as I mentioned, let's go ahead and say, include gravity and everything touching it. So what's touching it is the tension in the string or chain, which, as they said, is tilted out from the vertical at 28 degrees. And just in case you missed this, remember, this is alternate interior angle, so I'll have to go back to my geometry and say, well, that's 28 degrees, this one here is 28 degrees, and that's the one I'm going to really care about. And then, of course, we could, as you mentioned last time, talk about a z direction, but just like last time, we won't need it, so let me kind of leave it off the picture here just so that hopefully it'll be less confusing. But I'd say I'm done here then with the forces. I got gravity pulling it down, I got the tension from the string pulling it up at an angle of 28 degrees. And now I'm ready to write out my equations. I'm ready to go to step 3. But of course, like all of these, to write out the equation, we need to know what is the x and y components. We need a grid. All right, so I ask you again, what is the grid? And again, you can pick it anywhere you want. But I would suggest, since any of these circle ones, we're going to have a radial component along the way somewhere. And it would be nice if I don't have to worry about the x, you know, a component that is, it would be nice if my radial component was along one of my axes, so I don't have to take the mv squared over r and multiply by a sine and a cosine. And so I would suggest you find that center of the circle, and you set up a grid so that one of your axes are pointing along that direction towards the center of the circle. And so that axis is going to have an acceleration of v squared over r. And it doesn't have to have a component of it. And so that tends to make the circular ones make more sense. And I said the same thing really in chapter 5, where I would encourage you, and we did this when we had something going down the hill, that you took your axis and you tilted it, because you know when it slid down the hill, that was the direction of the acceleration. So always find out at least what is the direction of the acceleration and put your axis along that. It's really helpful, because that means the other axis is 0. So that being said, I can now write out my equations. I can say, all right, let's add up all the forces in the x direction. And in this case, since the x direction is the radial direction, then all of these forces must equal to mv squared over r. Exactly. And of course, this one I think is a little bit easier in terms of forces than that airplane one we just did, because in terms of the x direction, there's only a component of the tension that is in the x direction. And so this would be t sine of 28 degrees. And so that would be my first equation, x direction. And if I also do the same thing in the y direction, I would again argue that this seat isn't going up or down, it's going in a horizontal circle, at least once it gets to its, defined speed for the rest of the ride. I know as it's building up, the seats are actually then moving out and they are going up higher and higher. But I think they're trying to say at the point where they are spinning at a constant speed and the ride is just going around, then what is going on then? And what's going on then is we would have no acceleration in the y direction. So I can set that equal to 0. And as I look at the forces here, I would have a t cosine of 28 degrees. Because that one has a component up, and then I would have minus an mg, and that has to equal to 0. And so there's my step 3, writing out the equations. Which now leads me to step 4, and I'll do like the last problem. Let's do what I'll call 4a. Let's just plug in the numbers that we do have and see if we can solve this. Actually, they don't even look like coupled quite well. I guess they are coupled a little bit, but not too much. If you look at that last equation, this last equation would say that the tension would be equal to mg divided by cosine of 28 degrees. And maybe it's a good time to ask it again, does the tension equal weight? Sometimes it does, but not very often, and this is a good example where it does not. The tension is the weight divided by cosine of 28 degrees, I see after going through my analysis. And that kind of makes sense, because I would expect the tension to be more than the weight, because the tension has to not only hold up the seat or the child, but then also has to make it turn. And so this comes out to be more than just the weight. And then knowing that and putting it into here means that I can put mg over cosine of 28 degrees, then multiplying that by sine of 28 degrees, then equals to this mv squared over r. And so that's what I get when I solve that one and put it into that one, which again, as you can see, there's an m on each side, and so the ride is kind of a nice set of physics where the masses cancel off. And if you've ever seen the ride in action, you will see that every child, no matter how much mass is in that seat, and even the empty seats, all swing out the same distance and they all go at the same speed. And so you can see that canceling right here. And so continuing on with this, I would have the 9.8 times the tangent of 28 degrees on this side of the equation. And then, of course, there's the V, what I'm looking for. That's the part A. What is the speed of these swings? And then I need to know the radius, and that's worth filling in. What's the radius of this circle? And that's why I made such a big deal about it back here in step 1. Good physical picture.
4 plus 2.5.
Yeah. And so why don't we take that component and then add it to that, which, as you said, would be 4. They show the diameter being 8, so that means we've got 4 meters from the big circular dome at the top, and then we also have the length of the chain, which is 2.5 meters, but it would be the opposite component of the 28 degrees. And so then you can see that we know everything in this equation except for V. And well, I might as well do this one. Doesn't look too hard here. So 4 plus 2.5 times the sine of 28 degrees comes out to be a little more than 5. 5 times 9.8 times the tangent of 28. And then the square root to get the velocity leaves me with a speed of about a 5.2 meters per second. So I know I said I wasn't going to put them in there, but I thought it wouldn't take much time. So I go, well, that was not going to take much time. So there's the answer they were looking for. What's the velocity? And then I can go on to B, and B will go pretty quickly because it does say then, well, it says draw the free body diagram with the child in it and then find the tension. And I guess I didn't put a child in here, but at the same time I also didn't specify what exactly the mass was. So maybe just adding a child into this free body diagram. And then think of my object as the child and the seat. So there's my object. Wouldn't everything that I do be exactly the same? Wouldn't the free body diagram be the same? Wouldn't the equations be the same? The only thing that would be different is instead of the seat being a mass of, just by itself, 10 kilograms, I would have the 40 kilogram child plus the 10 kilogram seat. So we're talking about a 50 kilogram object in my picture. That's the only thing that's going to change. But if you'll notice, the m's canceled off anyways, and so the answer I'm going to get is exactly the same, whether there is or is not a child in there. So the speed with the child in there is still the same, but they ask for the tension, and so the tension is this number, and that number does depend upon mass, and so I'm going to put a 50 there times 9.8 and divide it by cosine of 28 degrees. Again, this one wouldn't take much time to get a number, so I'll actually get a number, but 50 times 9.8 and then divide that by the cosine of 28 degrees means that we have a tension of about 550 newtons. And so whatever chain we use to hold this right up, it better be able to hold 555 newtons. Otherwise it's going to break and there's going to be all kinds of problems. In fact, we should probably have it a lot more than that, just in case there's a bigger child or there's rust on it or all kinds of complications that can occur later on. And fortunately, chains are very strong, so getting that much tension out of a chain is a simple case. Well, I'll shift gears then, unless you guys have any questions with that. That's what I was kind of hoping to get to last time and do all the circular ones. Let's look at the other scenarios that you will come across as you start to do the homework. Let's look at the ones that are in an accelerating reference frame. That's probably the easiest one for me to show you, because if you recall during the lecture part of the accelerating reference frame, what did I say is kind of the best way here for the beginning student anyways to deal with accelerating reference frames? Get out and then do everything exactly the same. And so the same thing we've been doing, I don't need to show you anymore, but I do want to illustrate with at least one example, get out of the accelerating reference frame. So I put in my notes number 21. 21 is in this category here that says, here is a description, but the description of what is going on is from within an accelerating reference frame. And realizing it is within an accelerating reference frame will heed the warning that was given to you not only by me, but by Newton originally, way back when Newton proposed his 3 laws of motion, that this is working with just inertial reference frames. This only works in non-accelerating reference frames. And so when we went over Newton's 3 laws of motion, in fact, that was like the lecture even before the first test, was when and what are the limitations of Newton's 3 laws of motion. We said don't try to put them in an accelerating reference frame. That's not how they're designed to be applied. And Newton knew that, and that was warning number 1. The other limitation I'll keep saying, which Newton didn't know, is they don't work when you get close to the speed of light. And so when we get to chapter 39, we will add more to our physics, and we will add here with Einstein. So we like to say Newton's laws they're not complete. There's more to them. Fortunately, the speed of light is so fast that we don't even have to worry about changing our approach to a problem until we get to 10% of the speed of light. And so if you're designing a car or an engine or even a rocket, they don't go that fast compared to the speed of light. So Newton's laws work great. But 21 is an example. Here it says you got a 0.5 kilogram object that is suspended from the ceiling of an accelerating boxcar as shown in figure 6.12. Well, let me not turn back to that, but I'll at least draw the picture here. We saw this one during the lecture part where we took a train of some type and then the chandelier, I think it was, swung backwards as the train was accelerating out of the station. And so there's this little movement backwards. And of course, for you in the boxcar itself, watching it swinging back and then maybe even staying back while the train is accelerating would think there is some kind of force, some kind of fictitious force holding it back. And there is not anything holding it back. And Newton's laws aren't working right because you're in the accelerating boxcar. And so as I said, we've got 2 options at this point. We can either invent fictitious forces and then use Newton's laws with fictitious forces in an accelerating reference frame, which, like I said, sounds a little funny, but can be very useful. But I don't think it's the best approach to begin with now for you guys. Our best approach, I think, is to recognize that you could do that, but we won't do that quite yet. We'll just step out of the boxcar. And so knowing that we are in this boxcar, and it says taking the acceleration to be 3 meters per second each second, find the angle that the string makes with the vertical and the tension in the string. So I'll just take this with this idea of let's change the picture. Here's the boxcar, and we are now not standing in the boxcar, but are standing on, say, the platform outside on the train station, watching this whole thing go on, realizing that the whole object is accelerating. Because if you were in the boxcar, you might just think that it swung backwards and was not accelerating. Which is why we would have to adjust Newton's laws to take account of what is not really happening, to explain what is not really happening. And the best thing, like I said, is to kind of step out here. So I'm going to step outside here and say, let's take a look and let's analyze this problem from outside the boxcar and then do exactly the same thing we were doing. And so that's why I think it's only necessary to do one example from this category, is just step outside, and everything else then just like we've done before. And so just like we've done before, we start off with step 1. Got a good physical picture of what's going on? Train's pulling out of the station, accelerating with a value of 3 meters per second squared. Some object like a chandelier hanging from the top of the ceiling swings backwards at some angle theta. That means there would be some kind of tension in that string that is holding it, and that's the question. What is the angle it swings back at, and what is the tension in that string? That's the main idea of this particular problem as the boxcar goes forward. So I would take the next step and draw the free body diagram. And so if here's the object, I would have tension at some angle theta. I would also have the force of gravity mg, and that's it. Those are the two forces touching on it. I would go to step 3, which step 3 would then say write out the equations, and part of that is choosing a grid. We do know that the whole object accelerates 3 in a horizontal direction. My advice to you, both in Chapter 5 and here in Chapter 6, is to set up your grid along the direction of the acceleration. If it was a circle, then point it towards the center of the circle, because that's the mv squared over r. We did a bunch of those. If it's a straight line, as in this one, do it in the straight line that it's accelerating. And so I would set up a grid, and in this case would be the standard traditional grid, calling x to the right and y upward positive. And once I do that, I can begin to write out these equations, and I could say the sum of the forces in the x direction equals mass times acceleration in the x direction. And the second equation is to add up the forces in the y direction. That has to equal to mass times acceleration in the y direction. So if I take this and now begin to write it out, I will look at this and begin to see that the only thing in the x direction is a component of the tension. And so this is all the forces in the x direction, and I can set it equal to mass times that acceleration. In the y direction, the tension has an upward component, so I'd have to multiply by cosine of that angle. And then we have gravity down, but it does not move in the vertical direction. There is no acceleration in the y direction. Again, that was the whole advantage of picking a grid or an axis that was along the direction of the acceleration. So the other one was 0. And so there's no sine or cosine here, and there is even no number there. And that's nicer than having your grid along the direction of your forces. At least my view of it is that way. And so there's writing out the equation, and then step 4, solve it. And so let's put in the values we are looking for. They say find the angle and find the tension. And let's see, do they even give us the mass? They do, 1/2 kilogram here. I suppose my first step might not even need the 1/2 kilogram, because this one is set up perfectly, to divide one equation by the other, because then tension cancels with tension and mass cancels with mass. I guess in your math class you'd call this the elimination method, right? Although you probably did more of adding and subtracting equations in the elimination method than you did multiplying or dividing equations. But dividing two equations is really kind of nicer, especially in this case, because I will get tangent then of theta is equal to a over g, which a is a 3 and g is a 9.8. So grabbing my calculator, I can do this last step and solve for the angle. And so 3 divided by 9.8, and then the arc tangent of that answer gives me an angle of about 17 degrees. So there's half of the answer. How far does it swing back? 17 degrees. Knowing that, I can get the tension, and so this one, or that one, but I'll just do this one, tension, and this would be just like the one we did a moment ago, although that was the swing going in a circle, but this part of the equation was the part that wasn't the circular part, and so it makes sense that it comes out to be one and the same. But 0.5 times 9.8, then divided by the cosine, and I'll just do my last answer, which is 17 degrees, coming up with a tension of about 5.12 newtons. And so the angle's not much, and so it's not quite equal to the weight. This is a little less than 1, not by much. What is cosine of 17? Yeah, it's only 90.95, so it It's a little bit more than the tension, as it should be. We should have a little bit, a little more than the weight. Tension should be a little more than the weight, but not too much. Most of it, the tension is holding up the object, but there's a little bit more giving it the acceleration. And it makes a whole lot more sense when it's outside to say, hey, it is accelerating. And so the tension is more than the weight. And so there is my example of what to do when you have you're in an accelerating reference frame. Oh, let's try the last category. The last category is the one that I think involves a little more math, and maybe some math you haven't seen quite yet, so it's nice to show you. It's math that isn't beyond you by any means, but it's stuff that maybe you did do in your calculus class, but it might look a little different here because this is what I would call applied math. And so we are going to come up with an equation, and that equation is going to have derivatives in it, and we got to get rid of the derivatives. And so just to remind you from your calculus class, you learn this thing called an integral, also called an antiderivative. I don't know, did you use the phrase antiderivative? Yeah, some of you are saying yeah, so I'll take that to mean all of you. But just like if I had something that was squared, like earlier we had velocity squared, I would do the inverse operation, which would be the square root, right? And I take the square root to get rid of it. Same thing here. If I have a derivative, I would do the opposite and I would integrate it. And that's really what I want to show you, because watch as we set this up. Let's try 3 of these. Let's build up and try some different ones. 30 is the easiest one in terms of resistance. It's a black problem. It's one that doesn't really require us to answer everything about the problem. It just asks at one moment in time. Here's 30. It says the mass of a sports car is 1,200 kilograms. The shape of the car body is in such a way that the aerodynamic drag coefficient is 0.25. It also has a frontal cross-sectional area of 2.2 square meters. Ignoring all other sources of friction, okay, calculate the initial acceleration of the car if it is traveling at 100 kilometers per hour and now is shifted into neutral and allowed to coast. So we're going to disengage the engine here, all right? Again, maybe a good picture is going to help here. So here's, say, the road. Here is, say, the sports car. Going at 100 kilometers per hour. I'll put in that direction. And, of course, there are air molecules. And so the car has to plow through those air molecules. I think they're trying to say sports car and a fast speed, because remember, as we talked about resistance, we kind of need to give a category. Would this be resistance based on a slow speed, where the object just kind of moves through the air and funnels it around the object and then it goes back? Or would this object be going faster than that, in such a way that as it moves through the air, not only does it push that air out of the way, but it kind of drags a lot with it? Then I think you can see it's going to be the faster speed one. If you've ever been close enough to a car which goes by, you'll feel the air being blown at you. And so cars at this speed definitely drag air along with them. And so if I understand the problem correctly, step 1, I can move to step 2, the free body diagram. And I can say, all right, what is then the forces on this car? And hopefully the obvious one is gravity and everything touching it. So what's touching it? Well, obviously the road, so there is the road pushing up. What else? And probably the most important one here, what is it? The air, right? And so I will put that capital R we talked about, the resistive force. It's really kind of a Newton's third law. It is the car puts a force on the air to push it out of the way, so the air puts a force back on the car. That's the resistive force. And so there's the R. Now, we might argue about maybe some friction and some slowing down because of the tires, or maybe some speeding up because the engine is pushing the tires forward. Remember, we said there would be that static friction between the tires and the road that we debated last time about which way it would go. If you were stepping on the accelerator, I guess it would be friction giving you a forward motion. If you were stepping on the brake, or even just off of the brake, there would be what you would call engine braking. And then there would be a backwards force there. So that would be that resistive force. I mean, not resistive force, that would be some friction. However, if I understood the problem correctly, it said that the engine was, first of all, disengaged. So there's no way that it's pushing the car forward. And then it goes on to say that even though the engine's disengaged, we wouldn't even have engine braking, but we might have some resistive force of the tires rubbing on there, but they say that is negligible. And so let me take that out of my free body diagram. So at least, I make sure I understand what's going on here and what they're trying to convey here. And so the engine's been disengaged. So no engine braking, no throttle effect because of the engine. All of that is disengaged. It's shifted neutral. It's just coasting. But even a car coasting is going to have resistance on the tires, but that's probably minor compared to the air resistance. So that's the one that they ask us to leave there. All right, so good. I think I got it. I think I got a good understanding of the problem as well as the free body diagram that goes with that understanding. And those are the two important steps, the big ones there. Because now I can write out the equation. And of course, like any of these, first thing to do when writing out the equation is decide what is going to be your grid. And I would encourage you to always set up a grid so one of the axes is along the direction of the acceleration. In this case, I might even use the word deceleration. We like to stay away from the word deceleration and just give a direction to our acceleration. And in this case, I would say that this car is slowing down. It has an acceleration in the negative direction here, okay? But certainly my grid, my x-axis, is along that direction. All right, so I'm going to have a negative acceleration here, hopefully, when this thing slows down. All right, so I've hopefully picked a coordinate system so that I can write out these two equations. And then, of course, I could solve these two equations. So writing out the equation, I would say in the x direction, I have a resistive force in the negative direction. That is all the forces in the x direction. And that would have to equal 2 mass times the acceleration. And I won't even put x here because if I understand this right, that is the total acceleration of the car. It is then slowing down. Whereas when I do this same set of problem in the y direction, I would have normal minus mg, and then that would equal the acceleration in the y direction, but the car is not going off the ground or under the ground or anything like that, so it is level, and so there's no acceleration in the y direction. And in this case, then, the normal force does equal mg. So does the normal force always equal mg? No, it does in this case, right? I don't even think there's anything about the y direction I'm going to need to solve this problem, but again, just for completeness, that is my step 3, writing out the equation. Now I can begin to solve this. And so I'll put a negative here. And the question was, what is the acceleration, I believe, isn't it? Yeah. Calculate this initial acceleration. Now, maybe I'll finish writing out the equation to emphasize why does the author say initial acceleration. As you recall, we broke down the resistive forces into the 4 factors that would go into play of why there is resistance from the air. The big one we talked about first is the speed. And we talked about if something was going slow, it would be proportional to the speed. If it was going fast, it would be proportional to the speed squared. Because again, if you doubled the speed, you would hit twice as many molecules as a lower speed. And if you're dragging them along, you would drag twice as many along. So there would be 2 factors of the speed there. The other thing we said is as you move through the air, how much air you actually hit depends on that cross-sectional area of the vehicle and the density of it. And then, of course, how you hit them is based on the shape of the object. You can have a more aerodynamic object, which would then have a low drag coefficient because it can move through the air quite well, and it doesn't just do a blunt hit to them, kind of ricochets them off to the side. Or you can have something that is what we would call non-aerodynamic, and it just kind of bluntly hits them and has a much bigger number. And so we have all of these factors: how fast, what is the size, what is the material you're hitting, and what is the shape of the object as it goes through there. And so that was our discussion back into the lecture part. And I think we know all these. Notice then that the acceleration does depend upon the speed. So if this car is going 100 kilometers per hour, it's going to have an acceleration. But a moment later, as it slows down from 100 and now it's only going 95, does it have the same acceleration? No. And so that's what's going to make the math a little bit harder. Now we won't see that till the next problem because they just ask for what is it at that moment when you're going 100. What is it initially? So all those numbers I know, I can put these in. This is a 1/2. They said the drag coefficient is 0.25. The density of the air, I don't think they gave that directly, did they? No, and so we need to look that up here. But the author has it listed in the front or back cover somewhere in here. It's not front. It's not back. It's on Google. All right. And so it's 1.25 kilograms per cubic meter is the typical density of air. So let's find it somewhere. Now, I know it's somewhere in there, but there's the density of the air as we kind of move through it. Of course, that kind of varies with humidity and temperature. So you'll see anything from 1.20 to 1.3. I'll just kind of take the middle ground. Cross-sectional area, they just said that was 2.2 square meters. And so there's the cross-sectional area. The velocity now is 100, but let me watch my units. This kind of really brings us back to chapter 1 and also to the test. Watch your units. You got to convert your units and so that they all match here. And so he gives me 100 kilometers. So I'll change that to 100,000 meters. And instead of an hour, I'll do a substitution. 1 hour is the same as 3,600 seconds. So do a direct substitution and then square that. So H equals 3,600 S, right? And so there would be my speed in meters per second. The mass is 1,200 kilograms. And now the only thing I don't know is A. Solve for A. And maybe I should just kind of check my units here. But it looks like a kilogram is going to be on each side. They'll go away. And over here, if you look carefully, there's a square meter. And then this is going to be another square meter. So there's meters to the 4th. But I've got meters cubed downstairs. So that's going to leave me with just a single meter in the top. And then seconds squared leave me with what it should come out to be, right? Here is my checking my units, right? See if my logic is right, and then my unit should come out right. I know acceleration should be measured in meters per second squared, and sure enough, I have it. And of course, the negative is going to come down, and so putting these together, I have 1/2 times 0.25 times 1.25 times 2.2 times quantity 100, 1,000 divided by 3,600, close quantity and squared. And then all of that is now divided by 1,200. And so 0.22 meters per second squared. Negative, I should say. And again, makes sense. So I got the negative, I got the units, I got the acceleration at that moment. it'll change as the car speeds of the car changes, but they don't ask for all that. Again, that's why it's a black problem. Yeah.
I was wondering what the number was. That was kilograms per meter cubed.
Density of air.
Oh, is that like a known?
Well, it's something that was not given in the problem, and it's something that we do need to look up. I said it was somewhere in this front or back cover, but I can't seem to find it. But I know it's... Where is the density of air? Well, again, now that we live in the informational age, it's easy just to Google or ask Siri. She knows everything. Look at the density. And so we've got the densities. But that's where that came from. And obviously then it would be different if it was like in higher altitude. We made a comment about airplanes and why they would fly at such high altitudes, and there's why. The resistive force can be dramatically less if there's less density. And for fuel consumptions and economy reasons, you'd really want that. Okay. And if we went through air, we would need water, we would need to know the density of that, which brings me to 31. 31, I think, is a kind of a step up to this problem here. It's a little different also because it is not a fast moving one. It is a slow moving one. So instead of having velocity squared, I'll have just the v. It's not always so easy to decide, so your author will give you the extreme conditions. He'll say, something like a rocket ship or a race car or a fast speed skater, and all these things to imply we're going at a significant speed that as we move through the fluid that we're dragging things along, and they want you to use the v squared. Other ones, they'll say something to indicate it is at a slow speed, and I think that one has it in here. They'll start off with the word small. Spherical bead, mass of only 3 grams. So this is the weight of a penny. It's released from rest at time equals to 0 in a bottle of liquid shampoo. All right, now stop and think about what he's trying to say here. Besides the fact that we're dropping something in a fluid and it moves through, doesn't this all imply he's trying to say it moves slowly? You got a light object, a small light object in a thick goo, right? Don't ask why we're dropping it in a bottle of shampoo. That's a whole different question. But for whatever reason, we're dropping this bead in a bottle of shampoo. All right. The terminal speed. So remember we talked about how it would go faster and faster, but not indefinitely. Because it would faster, the resistance would get greater and greater, and until the resistance equaled the weight of it, then the net force would be 0. And then the object would fall the rest of the way down at that speed. That was what we called its terminal speed. Its terminal speed is observed to be 2 centimeters per second. So again, fast or slow here? Slow. All right, so not quite the same as we did in 30, but they're trying to make it a little bit different. Find A, V, and unfortunately, it goes to the next page here. Find the value of the constant B that is written out in equation 6.2. B, the time at which the bead reaches 63% of its terminal speed. Sounds like a funny number. We'll see the reason why 63% is picked. C, the value of the resistive force when the bead has reached its terminal speed. Okay, so there's a bunch of questions in there, but before we even try to answer the questions here, let's just ask ourselves, do we have a good physical picture of what's going on? And I guess I have this bottle of shampoo. And for whatever reason, there is a bead that is placed in there, and the bead begins to drop to the bottom. Okay. And they tell me a lot about it, particularly the terminal speed. They tell me the terminal speed is a very small 2 centimeters per second. And all of that was just trying to get to the point that this is not going fast. So that when I make this next step, free body diagram, and I draw the bead and I draw all the forces on the bead, what do I have? Well, there's gravity, mg. What else? And the whole point of this is what's touching it is the thick, gooey shampoo. Has what we'd call a high viscosity here. And so there's a resistive force. And that resistive force, at least in magnitude, is little b times v. And that's where that little b came into the question here. And that's what we saw when we worked out in lecture, that the resistive forces is proportional to the speed. And so again, notice I've used just the speed v, not v squared for this scenario. And that's it. The good part about the resistive forces is the math is hard enough that usually the physics part of it is pretty easy. And so we just got two forces. Gravity down, resistance up, end of story. There's no left or right here. So as I make the next step, step 3, and say let's write out the equation, again, I need to pick a grid. And I don't see much reason to change the direction of my axes, except for maybe the vertical. It does move downward. So will it be okay if I call downward the positive direction? I'll just make a switch and call down positive. Of course, it wouldn't matter. But since that's the way your author works out the solutions, I figure I should probably do the same, because I have a feeling that when I go through something in class, you do your best to understand it, but that's not complete. So then you hopefully go and read the book, and then hopefully they match. So I try to say the same thing. I try to use the same symbols so that whatever you don't get from me, you can get from the book. Oh, we got the videotapes this semester too. I forgot about those. So, or I guess I shouldn't say videotapes. The YouTube videos. There we go. Since they're not tapes anymore, but. At some point, you'll probably have to go back and review all of this as you get ready for the test. And so it's nice to see it in the same format, whether it's in the book or whether it's in the lecture. So I like that. So I'm going to use y going down, since that's what a positive, that's what your author does here. And now I can write out the equations. So if I write out the equation in the y direction, it would have to equal mass times acceleration in the y direction. And I'm not even going to put the x direction. There's nothing going on in the x direction. All right. But as I look at this, I would say that I have a force going down, there's nmg, and I have a resistive force that is equal to bv, and it is an upward, which is the negative direction. And that would have to equal to ma. And so there's step 3. Now here's kind of the new step, step 4, let's solve this. And when we go to solve this, you will see that we have one side of it, the left-hand side, which has a v in it. That's great. I would love to solve this equation for v. The other side of the equation, though, has acceleration. And acceleration then depends upon v in such a way that it is the derivative. And so on the other side of the equation, I also have v. Perfect. Right? I have an equation that's got v's in it. Love to solve equations with got the same variable. However, it's not just v, it's the derivative of v. So if this was an algebraic problem, you would know to merge those two v's together, right? And then solve it. Well, I would say the same thing in a calculus problem. Get the v's together and solve it. And so some of you may not have actually done this step before. So let's try a few mistakes along the way to see what works and what doesn't work. So help me out. How would you solve this equation? suppose the first reaction is just to integrate. And see, I love that, because what would happen over here on the right-hand side? Now, of course, when I say integrate, I should say integrate with respect to what? Yeah, and I would do time, because isn't that what an integral is, an antiderivative? Doesn't it undo the derivative? I mean, the reason I think about that first is I stand over here and I look at this and I realize, wait a minute, this gets undone. The fact that you are taking a derivative with respect to v and then integrating that undoes it. You could think of it this way. The dt's cancel off, right? And then you have an integral of m dv. And since m is a constant, you can pull it out, and then you just have an integral of dv, which is v. Yes, of course, exactly the whole reason I took an antiderivative was to get rid of the derivative. So that's all looking good, unfortunately. The other side of the equation, I run into some troubles. Because if I integrate this first term, I get mg, those are a constant, I can pull it out, and then I just have an integral of dt, and so that's a t. No troubles yet. I like that so far. But here's where I run into the troubles. What am I going to do here? Now, I heard someone say b is a constant, I can pull that in front. Okay, fine. I'll do that much. But that's the easy step. Here's the real problem. What am I going to do with v? Can I pull it out in front? No, it's not a constant. So what do? I can't integrate it, right? I don't know what to do. I'm stuck. So bad advice. Don't do that, right? You're stuck. You can't get there that way. But of course, maybe now you see what went wrong. What went wrong is I have a v that I'm trying to solve for, and in this part I'm trying to integrate it. Wouldn't it have been really nice had that v, which is giving me troubles, been over here where I have an integral with respect to v? So in your math class you probably heard this phrase, separation of variables. Put all the v's with the v's and put all the t's with the t's. And then you don't have this problem. I have this problem because I did not separate my variables, right? I have this problem because I'm trying to integrate with respect to time, but I have the variable v with it. This problem would have gone completely away had the v been over here with the dv, and then I would only have times over here and v's over there. Fair enough? So let's rewrite this equation, and now that we know the dilemma we just ran into, we will hopefully also now know the solution. So I will ask you, what should I do? Okay, I heard this. And it's a good try, but it really hasn't solved my problem. Because again, when I go to integrate, aren't I still going to get something like this? See, I really haven't put the v with the dv. All right, so no, I don't want that. I want the v with the dv. What do I do? Yeah, I think I heard it here. To get them together, we'll divide. Now, they're together, aren't they? That's what I'll call the magical step. That's what I'm sure you came across in your math class, or you're learning now in your Math 160, is how do you work on a differential equation? The easier differential equations are what we call separable, and that's what we're going to give you. The easy ones, the separable, the ones where you put all the v's on one side and all the t's on the other. And that's what this is. On the left-hand side of the equation, I just get the number 1. On the right-hand side, I get something that looks like this, but it is a giant little multiplication factor that has all the v's together in a big product. So the v's are with the v's. And for that matter, the t's are with the t's, although there are no t's in the equation, so there's just a 1. In fact, you can even think of this as then multiplying both sides by dt. So what I have is dt on that side of the equation, and I have an mg minus bv dv. And maybe now you can see it in what I really wanted you to see. And for some of you this is new, except maybe when I use the word separation of variables, you begin to see, oh yeah, that's what we did do in our calculus class. Because when you get all of them on one side, now you can just do an integral. If you look here, when I do an integral of both sides, I've got only t's here. I can do that integral. Over here I got integrals that just have v's. I can do that integral. I don't run into the trouble where I have both variables within the same integral, and I avoid that. So again, that's what I wanted to make sure I showed you here. And so that's the separation of variables. Now don't get me wrong, there's still a lot of math to do. And like I said earlier, I think these type of problems are more math intensive than they are physics intensive. And so those first three steps of writing out or getting a good physical picture, then doing the free body diagram, and then writing out the equations are actually pretty easy. It's the fourth step, then solving the equation, that is a little harder here. And that's what I'm trying to show you here, solving the equation. So I wrote out the equation in step 3, and now I'm trying to solve it. And the first big step, and then the rest of it I think you can do from here. I'll continue to go on because there's a lot more steps. But the big step I think was right here, separating the variables. Once I separated the variables, now I can do the integral. And of course, when you do an integral, you could do a definite or indefinite integral. Let's do a definite this time. Let's say that we are going to start at time equals to 0. And integrate to some moment in time. Maybe it's 1 second, maybe it's 2 seconds, maybe it's 3 seconds. But what I do know is then on this side of the equation, v starts at 0 and goes to some final speed v. And so I think most of the integrals we have done in this class have been indefinite integrals. So we had a constant of integration. When you set the limits, those limits are your constants. So the 0 is taking place of the constant. So I'm going to do a definite integral this time. And so this one here becomes the integral of t evaluated from 0 to t. The other one's a little more involved here. What's this integral? Maybe I'll start by taking an m out. So what is the integral of 1 over mg minus bv?
Log.
Natural log, right? And so this would be a natural log of mg minus bv. Not quite done. Don't forget the chain rule. Over negative b, right? And like any of these integrals, remember you can check it, right? Take its derivative. So if I take the derivative of the natural log of mg minus bv, doesn't that put it downstairs? Perfect. And then the chain rule would give me a minus bv on top, which is going to cancel with that one. So there it is. That is my integral. And I'm going to evaluate it from 0 to v. And so over here on the left-hand side, I get t. Over here, I get a negative mb. I'll just put those together because then I get an ln of mg minus bv, when I do that one, minus ln of mg. So like I said, this has got quite a bit of math in it, but again, nothing beyond you. Big step is the separation of variables. Then do the integral. And it's a little harder integral. We have a natural log. Okay. Of course, then once we get a natural log, we have to undo the natural log. So we have to take the anti-log or raise it to a power of e, whichever word you want to put there. I'll simplify it a little bit before I do that though. Let me move my negative m over b to the other side of the equation. So I'm going to move that over to there. I'm going to simplify the natural log and write it as mg minus bv over mg. That's a nice property about logarithms. You're subtracting them, you can change that to a quotient. And once I'm here, then I can take the anti-log, or which is kind of a dying word too, like an antiderivative. What do you guys call it? Exponentiate. And so I will raise it to a power of e.
E over m and not m over b.
Oh, thank you. I guess I forgot to invert my fraction when I brought it over. Minus b over m minus b over m. Yeah. Okay, good. And then, of course, the whole reason of exponentiating it here. Question.
How come it's ln of mg minus bv minus ln of mg?
Okay, so the integral is the ln. So I put v in place of v.
I see. And the here. Okay.
Yeah, right. Yeah. And so now I get just the mg over the mg minus the bv. And you can see where we're headed, right? We're eventually going to get equation of v. So let me solve for v by itself. And so I've got an mg times e to the minus bmt equals an mg minus abv. I'll just move the negative to make it positive, and then I'll move this to the other side, making it a negative. I'll even divide both sides by the b and factor out an mg over b. And now I think you'll see what I was saying. There's quite a bit of mathematics into solving this one, and so step 4 took the longest of our 4 steps. We wrote out the equation, and then we solved the equation. But we've got some calculus, and we've got some algebra 2, and then some algebra 1 that we've got to put all together. And so now I have this equation that shows me what is the velocity of this bead as it is dropping down through the shampoo. And in fact, it's probably worth putting a graph on the board and say, what does this mathematical function look like? Well, this is a decaying exponential that has been inverted and offset. So decaying exponentials look like this. When they're inverted, they look like this. And when they're offset, they shift up. So that would be my velocity as a function of time. You could even see the limit. After a long period of time, what would happen here? That goes to 0. So what would be my speed after a long period of time? And so this should exponentially obtain mg over b. And so it asymptotically approaches a terminal speed. And that's what we had said conceptually, that there would be a terminal speed. And so now we have just shown that the terminal speed is this mg over b. And in fact, that helps me now answer the question, because although I've erased it from all my work here, they told me that the terminal speed was 2 centimeters per second. So looking at this, I know that the terminal speed being 2 centimeters per second, which I'm going to write as 0.02 meters per second, is then equal to mg over b. and the M is the 3 grams, and G is 9.8, doesn't that mean I can find the value of B? And that was one of the questions that was in here. What is the resistance? It was the first question. Find the value of the constant B in the equation. And so B would be 0.003, and that should be kilograms, times 9.8 meters per second squared, divided by 0.02 meters per second. I'll start with the units. You will see then that a meter and a meter cancel, and a second cancels with a second. And so we're going to have kilogram and second when we're left over. There's the value of B. Hopefully that makes sense, because the resistance itself would be B times V. So if you have units of kilogram over second, and then you multiply it by a velocity, meters over second, you get units of a Newton, and that's what we would expect this to come out unit-wise. So this is the correct units for B. Numerically then, I can get my calculator and say it is 0.003 times 9.8 divided by 0.02, and I get 1.47. And so maybe I should emphasize in this. It's been a long problem, but aren't we really doing the same thing? Right? Good physical picture of what's going on. Free body diagram. Write out the equation, solve the equation. Now granted, solving involved a little more calculus, so we've done a little more work, and I think this, you will notice, I think this chapter is a little bit harder than 5, and 5 was a little harder than 4. Last time I asked you if it was looking harder, you guys said no. So maybe I'll ask again, is it looking any harder? Or? Okay. Some people are saying yes. Okay. All right. And so it does build on itself. But really what is harder is that I think in this case we've just gotten to some math that is not beyond you, just you're not as familiar with here. But I'll say it again. Step 3, write out the equation. Step 4, solve the equation. This one just involves some calculus. And so there's my first answer. Let's go on. What was B? The time at which the bead reaches 63%. Now, at first that sounds like a weird number. 63%. Why would anybody ask about 63% of the terminal speed? Well, if you don't already know, it's probably worth committing this to memory. We see it a lot. It happens a lot in nature. It's a natural process. They're called the natural logarithms, the natural exponents. Why do we call them the natural exponents? Because they show up so much in nature, right? Isn't that what we just did? I mean, we didn't do anything fancy, and all of a sudden we got an equation that has an E in it. And I guess I erased the equation. I should have left it up there. So V equals mg over B, 1 minus e to the minus B over m. Yeah, let me get the order right this time. And so that's the equation. And not a surprise, it has a natural exponent in it. We could do rates of cooling, and we'll get natural exponents. We could do radioactive decay, population growth. All of these are natural functions that change and have a natural exponent. We'll see that next semester when we get into our electronics, and we'll have capacitors and inductors that we energize and they de-energize, and the rate at which they energize and the rate at which they de-energize and the rate at which, well, the list goes on. But a lot shows up naturally, and hence the name natural exponents. And so it's just the way nature is. It's too bad nature made it an E, an irrational number. There's 2.718, blah, 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 blah. But that's what it is, and so that's what we got to live with it. Now, I say all that because, do you know what e to the negative 1 is? Probably not. Learn it. It's 37%. Because what is 1 minus e to the negative 1? 63%. What did they ask me for? 63%. It naturally shows up in all the problems we do. And so not a surprise they ask for 63% of the terminal speed. So knowing that information, watch this. Here's what I have. I have this equation where the velocity equals mg over b, 1 minus e to the minus bm over t. And so what they're saying is find 63% of the terminal speed. We already said the terminal speed not only had a value of 2, but it was equal to mg over b. So this side of the equation is 63% of mg over b. Well, mg over b's, they're on both sides. And so I have 63% of 1 minus e to the minus b over mt. Does that even look close to like this? It does, doesn't it? Right? Doesn't that tell me then that e to the minus b over mt is equal to 1 minus 63%? Or 37%, right? Look, what does that tell me here? Do I need to get out my calculator and take the log of this, or is it so obvious? Doesn't this whole thing minus b over mt equal -1? Isn't that the whole point I'm trying to say there? Right? E to the -1 is 37%. All right, I'll get my calculator out. Natural log 37% -1. Okay? And so it's a good number to know. You'll see it a lot. And this might be the first time you've seen it so much in a physics class, but you'll see it in chemistry, you'll see it in biology, you'll see it in all kinds throughout the rest of this 3-semester course here. So you can either just get out your calculator and figure it out, or just know that's why people keep asking. You see, the reason we ask it that way is, would it make any sense to ask, how long does it take to get to terminal speed? Not a good question. How long does it take to get to terminal speed? Forever. It never really quite gets there. And so to be a little more accurate, we need something more appropriate to discuss. So when something is cooling down, we never say, how long does it take to get to room temperature? We say, how long does it take to cool down to 37% of the difference in their temperature? How long does it take for a capacitor to discharge? Terrible question. It takes forever. It's a really good question to say, how long does it take before the capacitor discharges to 37%? Or it charges up to 63%. And so the 37, the 63, very useful numbers when they come to the math associated with the math and science. How long does it take to completely get to terminal speed? Useless answer. Forever. How long does it take to fully charge a capacitor? Forever. Useless question. How long does it take for the chemical reaction to finish? Forever. Useless question. But how long does it take for 67% or 63% of it to finish? That can be answered. And give us something that has meaning. And so when it comes to science and engineering, it's the natural logs that show up. And so we got to ask our questions a little bit different. We have these asymptotes. And this is just one good example of that. That being said, then, we can now solve this for time. The time it would take would be t equals, and I guess we would have, well, the negatives would cancel off, and I'd get an m over a b. The m is 0.003 kilograms. The b is 0.145 kilograms per second. So the units work out to be in seconds, as I would expect. I would be surprised if it was anything different, but I should check my units, okay? And then the 0.003 divided by the 1.47 comes out to be 0.002 or 2 milliseconds. So it doesn't take long to get to 63% of the terminal speed. As you would expect, you can imagine dropping a bead actually in this soapy mix. You would probably look like to you it just went right to terminal speed and then went the rest of the way down at terminal speed. Of course, never really quite got there to terminal speed, but it would get really darn close to terminal speed in a very short amount of time, and most of the motion would be, you know. They don't ask it, but could I get the acceleration of this bead? Yeah, how? Take the derivative. You have velocity. You're not going to forget. Hopefully what we learned in chapter 2, take the derivative. Right? Take the derivative of that. You'll get acceleration. Could I get the distance that the bead traveled? How? Integrate that. Right. Perfect. Right? It's a non-constant acceleration. And you could tell me something like, after 18 seconds, how far did the bead travel? Assuming it hadn't hit the bottom yet. Right? And so we can put some numbers in there. Well, maybe I spent too much time here on this one. Let's go to 34. Oh, did we finish all these? Whoa, no, one more. See, easy one though. What is the value of the resistive force when the bead reaches terminal speed? Okay, well, I hear two options. One of them is we could take the value of B, since we just calculated that in question A, and we can multiply by the terminal speed. And true. But I was looking for an easier way, which I also heard. What would we know at the terminal speed? Maybe going back to the free body diagram, realizing that at its terminal speed, the resistive force equals the weight of it. Right? That's why we have a net force of equal to 0. So just as valid option is to take the weight of the object, which would be its mass, 3 grams, times 9.8. And so hopefully I will get the same number doing either option there. And so there's the last part of it. Well, one more, and because let's do a fast speed and do the same type of calculus. We'll just do it a little faster this time, now that you're experts with the calculus we just learned. Let's try 34. 34 I think is even a little bit easier. It's the same logic, but now we have something moving fast through a fluid instead of slow moving through a fluid. But let's go through those same 4 steps, and particularly that last one, solving the mathematics. And so step 1, got a good physical picture of what's going on. Step 2, draw the free body diagram. Step 3, write out the equation. And then finally, step 4, solve the equation. Hopefully, the equation won't be hard to solve, but sometimes they are, like this one. And so one's involving air resistance, because they have speed involved, and that involves usually then solving a differential equation. They are a little bit harder to solve, I think, which is why I said back in chapter 5, the author is going to start with the easy friction, the solid on solid. And then we divided those into 2 categories, the kinetic friction and the static friction. And now we've elevated past that. Now we've elevated to, let's look at the friction between the object and a fluid. And then that falls into 2 categories, a slow and a fast one. So let's do the fast one here. Let's read 34 here together. It says, consider an object in which the net force is consider an object on which the net force is a resistive force that is proportional to the square of the speed. So they just lay it right out there. You don't have to figure out that this is a fast speed. They're going to tell you it's a proportional to the square of the speed. For example, assume that the resistive force acting on a speed skater is given by this equation. And he changes it a little bit. Maybe I should just kind of rethink that. We've been talking about it in the book and in class, that the resistive force is, and we put a 1/2, we put the drag coefficient, we put the density of the air, we put the cross section, and we put the velocity squared. That's what we just saw in problem 30, and that's how we did the lecture on it. Your author kind of has simplified this a little bit and says, let's group this together as a K. I suppose, though, he says that if these are speed skaters, some people are bigger than others, and so their cross-sectional area might also be related to their mass. So he puts all of this together and calls it a KM, saying that roughly people have the same shape. They're each doing the same race, or whatever the density is. If it's ice skating, I would kind of guess it might be quite a bit above sea level here, but whatever that density is, that's the same. But skaters do have a different cross-sectional area. There's bigger people and small people, so we could have like the, little kids racing and then the adults racing, or even we could have big adults and little adults. So I think that's what he's trying to say here, is that let's remodify that. He calls it then an F instead of an R. But that's all he's really done here. So it hasn't really changed anything, but it's worth talking about it. It says where K is a constant and M is the mass of the skater. Now what it says here is the race is ending. The skater crosses the finish line in a straight line race, so no turning involving, okay, this is not a circular problem, this is a straight line problem. Crosses the finish line at a speed of V0. And so if you've ever seen like the Winter Olympics and you watch the skaters, you'll see, I mean, they're working really hard, and you get to that finish line and you're tired, so you rest on your knees and you just kind of come to a gliding stop here. And so that's what's happened here. A straight line race, finishes the race at a speed V0, and then slows down by coasting on the skates. And so again, I think the author put the skates because we said, well, we can ignore friction. There's no friction in the ice, or at least very little. And it's a speed skater, so we know it's proportional to the square of the speeds. All right. Show that the skater's speed at any time after crossing the finish line is given by this equation. All right. So, solve the equation. Well, let's give it a shot. We got, what, 8 minutes? And so maybe I should do it a little bit faster than the one before here. But I'll start with the first one. Do we got a good physical picture of what's going on? Right? Here's the ice. Here's the skater. Yeah. Okay, all right, so we got the speed skater, and they cross that finish line, right? And now they're going to coast. And so if I do the free body diagram, and just to save a little bit of time, I will put the free body diagram just kind of right on top of this. There would be, of course, the normal force from the ice lifting up on the skater. There would be the gravitational force pushing down on the skater. But the one that is relevant to us is there would be some resistive force as the skater has to plow his way through, or her way through, the molecules that are in the air there. So they hit those one. They hit them pretty hard. So it's proportional to the square of the speeds. So again, as far as the problem goes, I think those are the easy steps, if you will. Good physical picture of what's going on. Free body diagram. Even writing out the equation is probably the easiest step. It's solving the equation that's going to be the big one here. So step 3, writing out the equation. And again, like all of these, to solve the equation, you need some kind of grid, the x and y axis. I would say let's look at the forces in the x direction. That would have to equal mass times the acceleration in the x direction. And again, in the interest of time, let me not even do the y direction, but the one that's relevant here is the x direction. And so what I could say here is I have a resistive force, which your author is calling F. All right, so that is what is pushing in the x direction on the skater, in the negative direction. So the equation F with a negative. Then that has to equal to ma. And so let's write it in the terms that he has it. He writes it in a k, an m, and a v squared. Here is an m. And then again, like we did on the last problem, let's write a as the derivative of velocity so that we can see we have an equation that has v's on both sides. And like any equation that has velocities, and just like the last one, put the v's all together, put the t's all together. If it's a differential equation, we call that separation of variables. And if it's an algebraic equation, we just say we are combining like terms. We are putting x's with x's and y's with y's. But in this case, you can see then that because I don't have two terms to divide by, I think this is a little bit easier when I ask the question, how do I get the v's together with the v's? And I will divide both sides by v squared. There's also an m on each side, which I think was part of the reason why he thought it would be nice to write out the equation, not in terms of the shape and the density and the cross section, but in terms of everything else plus the mass added to it. So they cancel off here. And so what I have so far is a negative k on this side of the equation and a 1 over v squared dv dt. And I'll do one more step before I actually do the integral, and that is to multiply both sides by dt. So again, we have, like any differential equation you come across, at least the simple ones. When you guys take Math 220, you'll do some harder ones because not all equations are separable so nicely. But the ones we will do are, and so we have separable. So we put everything with the t on one side and everything with a v on the other side. And so there is our differential equation. So that's the first big step. And so now this is the second time you're seeing it. Most of you are shaking your heads like, okay, I get it this time. I see what you're after. You write down the equation and it has a derivative in it. I've got to separate the variables. Once I separate them, now I have to integrate them. And again, we can do a definite or an indefinite integral. The speed skater starts at a speed of v naught. I'm tempted to do an indefinite just to show you it works out the same. But to be more consistent, why don't I do it the same way that I did the other one? Why don't I go from a time 0 to t? And so 0 is when the skater crosses the finish line. And so this is going to be the speed some time later. So the speed is going to go from some speed v naught, not 0 this time, right? Last time, the object started at 0 speed, but this time the object is starting at a large speed, v naught, and then slowing down to some v. And that's the equation they're asking for me to come up with right here. What is the speed as a function of time? And it has a v naught in it. So this calculus is a little bit easier here. And for that matter, this calculus is a little bit easier. What's the integral of this one? Yeah, negative 1 over v. And so it's not a natural log, and then we don't have to then combine the natural logs and then take the anti-log to get there. And so when I put this into here, I get minus kt here. And over here, I get a minus 1 over v minus a negative 1 over v naught. And of course I need to solve this for v. So I've got a little more algebra to do. I guess in the interest of time, I'll just move this over and make it positive. I will take this one and move it over here to make it positive. Those two negatives are already a positive, and so I have that. Now I want to reciprocate those to solve it, but before I do that, let me get a common denominator. And so this is ktv naught plus 1. And so then I take the reciprocal of both sides, or raised to a power, or what some of you may call the upside down theorem. At least that's the way I learned it back when the dinosaurs still walked on the earth in my geometry. If you can take both of them and turn them upside down, you reciprocate both sides. But now I think I have it. There it is. There's the v naught slash, and then there's the 1 plus k and v naught and t, and so I did it. So algebra and the math was a little bit easier than the slow speed one, just because of the way math works out. But it's still step 4, solve the equation. All right, well, I guess we're done for today. We didn't get to start into chapter